Welcome to this video on the discrete Fourier transform. By the end of this video, you will be able to calculate the discrete Fourier transform of given data sets. You will be able to analyze that data using the power spectrum, and you will even be able to manipulate data using this discrete Fourier transform method. Now, the difference between the discrete Fourier transform and the Fourier transform that we looked at before, and where the equations to calculate the amplitudes are given here on the right, was that instead of having the analytical function g of t that we're trying to transform for the discrete Fourier transform, we have that function approximated by a set of discrete data points, so pairs of tn and gn. But the task still remains. We are trying to find these amplitudes a0, ak, and bk. So we can no longer, for the discrete Fourier transform, evaluate the coefficients using these shown analytical integrals. But so what? Let's just integrate these integrals numerically using the discrete data points that are given to us. Now there's a prerequisite for this to work, and the prerequisite for the formulas that we're going to derive is that we must have the data given at n+1 equally spaced data points in the periodic interval from 0 to uppercase T, and remember uppercase T was the fundamental period. Because the data points have to be equally spaced, we can calculate the time between data points, delta T, which is just the fundamental period, divided by the number of subintervals, that is uppercase N. And the data has to be periodic, which means that the last data point at n+1 has to be equal to the first data point value g at 1. So let's evaluate these integrals, and let's use the composite trapezoidal method to do these integrations. So that means a sub naught is equal to 1 divided by the fundamental period t. And I'm just going to replace that integral with the composite trapezoidal method, which was take the value of the function at the first data point plus 2 times all the intermediate data point values gn, from little n goes from 2 to uppercase n, and then plus the value at the very end, the g uppercase n plus 1. So let me copy the first part over, and then because the data is periodic, meaning that the last data point value has to be equal to the first data point value, this is just 2 times the first data point value g1, plus this sum here 2 times all the other data point values, with the exception of the very last data point, because that's included in and equal to the first data point. Now, my delta t was defined as the fundamental period divided by the number of subintervals. So I can just substitute this in here, right? If I substitute this in for delta t, I'm just left with 1 over the number of subintervals, uppercase n. And then the half gets multiplied into this sum here. So I'm just left with the sum of all the data point values from the very first point to the next to last point n. So the sum does not include the very last data point. Okay, so that's my a0. Let's move on to the amplitude of the kth cosine wave. So that formula is a sub k is equal to 2 divided by the fundamental period. And I'm again using the composite trapezoidal method. So times delta t over 2, step size, subinterval size divided by 2, times whatever the integrand is at the first data point, so that's g at 1, times the cosine of k omega t at 1, plus 2 times the integrand evaluated at all the intermediate data points, so gn, right, where n, little n goes from 2 to uppercase n, times the cosine of k omega tn, plus then 1 times the integrand at the very last data point. Now let's use the definition of delta t again. So that gives me now 2 divided by the number of subintervals uppercase n times. Again, the first data point value has to be equal to the last data point value. And even though the times t1 and tn plus 1 are not equal because I have the fundamental angular frequency omega in here in the cosine values evaluated at t1 and tn plus 1 will be the same. So I can combine them to a single term, 2 times the first value. And then I have the other 2 times the sum values in there. So every function value, every one of these integrands appears twice. So that then can be combined into the sum from little n equal to 1 to uppercase n, the number of subintervals, time of the g, the data point value at the nth point, times the cosine k omega t, t being the time at the nth data point. And then finally, the amplitudes of the sine waves. B sub k using trapezoidal method. So it's 2 divided by t times interval size delta t over 2 times the integrand evaluated at the first point. So g1 times sine of k omega t1 plus 2 times the integrand evaluated at all the intermediate points plus the integrand evaluated at the very last point gn plus 1. And now again using the fact that delta t is equal to the fundamental period divided by the number of subintervals, I can combine that to 2 divided by uppercase n. And using the fact that the first value is equal to the last value, those can be combined to do 2 times the first value's term combined with all the intermediate terms gives me just the sum of g evaluated at little n, where n goes from 1 to uppercase n, times the sine of k omega tn. So that's just evaluating these integrals using the composite trapezoidal method. There's one final challenge though. In the Fourier transform, we had infinitely many wave numbers. The wave numbers went from 1 to plus infinity. Now, because we only have a finite number of discrete data points, can k really go to infinity if we only have uppercase n unique data points? Remember, there's n plus 1 data points in total, but the data has to be periodic, so the n plus first value is equal to the first value, so there's n unique data points only. Well, there's something called the Nyquist frequency, which means that we need at least 2 data points per wavelength to identify a sine or cosine wave. That means that if we have n unique data points only, our wave number can at most go up to number of unique data points divided by 2, because I need 2 points per wave number. So my maximum wave number, k max, is equal to n over 2. So in the sum up here, where I represent g of t, I cannot go k equal to 1 to infinity. I can only go k equal to 1 from 1 to n over 2 for the discrete Fourier transform. And there's one additional pitfall that comes from linear algebra. If the wave number is equal to this maximum wave number, the orthogonality condition to calculate the coefficient a sub k is slightly different. And the only difference being, instead of 2 divided by n in front of the sum, the amplitude of the cosine for the maximum wave number, ak max, is equal to 1 divided by n. It's just 1/2 of this ak value. Okay, so let's do a challenge question that kind of asks about the application of the discrete Fourier transform. So here's the scenario. The pressure in a duct fluctuates periodically, and provided that measurements are taken at equal time intervals and only the below options are available, how many measurements per second must be taken to identify a frequency of 400 Hertz using a discrete Fourier transform of the measured pressure? So here are the 4 options. Option A is you would have to take 100 measurements per second. Option B is you have to take 400 measurements per second to identify a frequency of 400 Hertz. Or you should take 1600 measurements per second to identify the 400 Hertz signal. Or none of these options, 100, 400, or 1600, would work? Please make your choice. So the correct answer is that you should measure at 1600 Hertz, provided that these are really the only options that you have available. And the reason for this is that 1600 measurements per second is the only option that provides the necessary 800 measurements per second to identify the 400 Hertz signal. And that comes from the Nyquist frequency. I need 2 data points per wavelength. If my signal has 400 Hertz, in order to be able to identify this, I need at least 800 measurements. And the only option here that provides me at least 800 measurements or more is option C. Okay, so now let's talk about the power spectrum. The power spectrum combines the amplitudes of the sine and the cosine at the kth wave number. So the power spectrum value P is a function of the wave number k, and it's defined as a half ak squared plus bk squared divided by uppercase N, the number of unique data points. And this power spectrum indicates how large the contribution of the wave number k is to the overall signal g of t. So here's an example. A signal y was measured over a period of uppercase T equal to 1 second using 101 samples. Okay, and those data points are just generated from this given analytical function y of t over here. So I have a total of 100 unique data points. And if I were to plot this signal, here you'll see this periodically repeating signal over the fundamental period of t equal to 1 second. Okay, so if I calculate the power spectrum of this equation, right, I do the discrete Fourier transform, I will calculate the a sub k, the b sub k, and I then calculate for every wave number k, that goes from, right, the k goes from 0 to 50, 100 unique sample values, means that because of the Nyquist frequency, my k can go up all the way to k max equal to 50. If I plot that power, p sub k, as a function of k, I get the following graph here. So let's look at the biggest spike here, right? That is the highest value of the power. So this is supposed to be the wave number that contributes most to the signal y of t. And if you look at the k value down here, it's a little bit hard to pick out. The k there is 7. And if I look at my analytical function here that generated these data points, you'll see that this is the sine of 7 omega t. So there's my wave number 7. And that 10 there is actually the sine cosine, right, with the highest amplitude. It's the most important signal, most important contribution to the y of t. The next would be, right, from these peaks over here, would be the value at k equal to 17. See, that's the next highest peak, right? And we'll look here at the analytical solution, or the analytical function up here. That is the sine cosine with the next larger amplitude. And then finally, for k equal to 1, there's a tiny little peak up here, indicative, right, consistent with that amplitude being smaller than all the other prior two amplitudes. Well, but then we have this additional cosine here at a k equal to 3. And if we look at this plot over here, we don't really see anything. Right? That's because the amplitude is quite small. It's just 1 over 100. So if we want to pick up these signals, it's helpful to plot the power spectrum in a semi-log plot, meaning we do the power axis, so the vertical axis, in logarithmic scale, and we keep the wave number k in linear scale. And then if we look at this here, right, then in this logarithmic scale, this signal at k equal to 3 actually shows up just because of the logarithmic scale. Also, interestingly enough, right, you'll see that the power never really goes to 0 for k values that are not part of the analytical function. Instead, it hovers around 10 to the negative 30. Now, why is that? Well, it's because when we do these numerical integrations, we are never exact. We always have round-off errors. And this round-off error around 10 to the negative 30, 10 to the negative 32, if you remember, the smallest difference in numbers that a computer can represent with double precision is about 10 to the negative 16. The power spectrum involves the square of this amplitude, so that puts the numerical round-off error around 10 to the negative 32, 10 to the negative 31. And that's what we see here in the logarithmic plot, the semi-log y plot, that those values not being 0 is because of round-off errors. Now, one more challenge question. So let's say a probe measures temperature in time intervals of 0.01 second for a duration from 0 seconds to 5 seconds. When the power spectrum is plotted using the discrete Fourier transform, the power value at k equal to 1 corresponds to what frequency of the signal? And here are your options. Option A is the frequency would be 0.2 hertz. Option B, the frequency is 1 hertz at k equal to 1. Option C, the frequency is 5 hertz. Or option D, the frequency is 100 hertz. Please make your choice. So the correct answer is that the k equal to 1 wave number corresponds to a signal of 0.2 hertz. Now, why is that? Well, we've taken signal, right, from 0 seconds to 5 seconds. So what's the fundamental period? Well, the fundamental period is the duration of our signal taking. It's 5 seconds, okay, which means that the fundamental frequency, which is 1 divided by the fundamental period, is 1 over 5 hertz, 1/5 hertz. Now, k equal to 1 corresponds to a frequency, right? And what frequency is that? If I have a wave number of k, that corresponds to the frequency of k times the fundamental frequency. So if k is equal to 1, I have 1 times the fundamental frequency being 1 over 5 hertz. That's equal to 0.2 hertz. So in this case here, if k equal to 1 in a power spectrum corresponds to a frequency of 0.2 hertz. Now, what can the discrete Fourier transforms, what can they be used for? Well, they can be used to analyze the frequency content of a signal. So we could find the important frequencies in a signal that relate to some behavior of interest. So for example, that could be engine knock, right? Some frequency audio signal. We can also manipulate the signal, right? Once we've done the DFT and we have the individual amplitudes, we can change the amplitudes of specific frequencies, right? We change the A case or the B case. We can make them stronger by multiplying them by a factor larger than 1, or we can make them smaller by dividing by a number larger than 1. So examples for that are high-pass or low-pass filters. In those cases, we actually set the amplitudes below or above a given frequency to 0 and filter out that portion of the signal. Now, once we've modified the amplitudes in order to reconstruct the actual signal, right, we have to then calculate g of t, a new g of t, by doing this sum over here, right, the discrete Fourier transform in reverse, where we reconstruct the signal as a naught plus the sum from k equal 1 to n over 2 of ak, my new ak cosine k omega t, plus the corresponding signal for sine k omega t. Now, we'll do some applications of that in the recitation, and we'll actually do some coding of how to do the DFT in the recitation. So here's a plug so you can look forward for the recitation. Thank you for watching.